What does it mean to be home? For us, for humanity, home is a planet of impossible blues and swirling whites, a world teeming with life. But zoom out and our home expands. It becomes a system, a gravitationally bound family of worlds, all dancing to the rhythm of a single star, our Sunday. Every planet, every moon, every tumbling asteroid and shimmering comet within this vast architecture is a sibling born from the same swirling cloud of gas and dust some 4.5 billion years ago. They are made of the same fundamental stuff. They are in a very real sense times ours asterisk. This shared ancestry, this common origin, is the unwritten law of our cosmic neighborhood. It defines the familiar, it defines the known. Yet this profound connection carries with it a paradox of staggering scale. For while every atom in your body was forged in the heart of a long-dead star, linking you intimately to the grand cosmic story, you are also profoundly, almost perfectly isolated. Our solar system is a celestial island, a solitary archipelago of light and warmth adrift in an ocean of unimaginable emptiness. Between our sun and the next star, Proxima Centauri, lies a void so complete, so utterly immense, that it defies all human intuition. This is the Great Dark, the interstellar medium, a realm where distances are not measured in miles or kilometers, but in the relentless passage of light itself across years and millennia. To truly grasp this isolation, you must journey to the farthest frontier of our sun's dominion. Go past the rocky inner worlds, past the colossal gas giants and their intricate courts of moons. Fly beyond the Kuiper belt, that scattered disk of frozen relics from our system's dawn. Keep going out into a darkness where the sun has shrunk to become merely the brightest star in a sea of countless others. Here, 1 trillion kilometers from Earth, you would find yourself enveloped by the Oort cloud. It isn't a cloud of water vapor, but a ghostly spherical shell of trillions of icy bodies, each a frozen time capsule from the birth of our solar system. This is the edge of our celestial island, the final shimmering shoreline of the sun's gravitational grasp. These comets are our most distant relatives, bound by the thinnest of gravitational threads. For eons, we believed this was the absolute boundary. Everything inside this crystalline sphere was family. Everything outside was an untouchable, unknowable wilderness. We could gaze at the distant lights of other stellar islands, but we could never hope to receive a visitor, a piece of flotsam washed ashore from those impossibly remote places. The currents of the cosmic ocean were thought to be too slow, the distances too profound. Any object cast out from another star would surely wander the darkness for eternity, a lonely ghost never to find a safe harbor. This was a fundamental assumption, a pillar of our cosmic worldview. And then, on a quiet Wednesday in October of 2017, that pillar was shattered forever. It arrived without warning, a phantom streaking through our system on a trajectory so bizarre, so alien, it could only have come from the deep. Telescopes in Hawaii caught the first fleeting glimpse of a faint point of light moving with astonishing speed. Astronomers raced to calculate its path, their computer models churning through the data, trying to force it into a familiar, predictable orbit around our Sunday. But the numbers refused to cooperate. The object's trajectory wasn't a gentle closed ellipse like that of a planet or an asteroid. It was a searing hyperbolic slash, an open-ended path that screamed of an origin far beyond our shores. This was it, the first one, a messenger from another star. We named it One Eye, Oumuamua, a Hawaiian word meaning a messenger from afar arriving first. It was an apt name for a discovery that felt less like an astronomical observation and more like a first contact. But this messenger was maddeningly enigmatic. As we scrambled to train every available telescope on this fleeting visitor, it revealed itself to be unlike anything we had ever seen. It wasn't a spherical comet venting a beautiful tail of gas and dust as it neared the Sunday. Instead, spectral data suggested it was an object, perhaps 10 times longer than it was wide, a dark, reddish, cigar-shaped anomaly, tumbling end over end through the void. It was a bizarre cosmic spindle, a sliver of another world, and its behavior grew stranger still. As Oumuamua whipped around the sun and began its journey back out into the interstellar darkness, it did something that continues to haunt physicists and astronomers to this day. It accelerated, not by much, just a tiny persistent nudge, but it was a push that the sun's gravity alone could not explain. Comets accelerate like this all the time. As they warm up, jets of gas burst from their surface, acting like miniature rocket engines. But we could see no such outgassing from Oumuamua. There was no coma, no tail, no evidence of the celestial blowtorch we would expect. It was moving under its own mysterious steam. What was it? A new type of comet? One that vented its gas in a way we couldn't detect? Was it an impossibly thin solar sail, a piece of alien technology pushed by the radiation from our own sun? Was it a nitrogen iceberg, a fragment chipped from Marso? A Pluto-like world in another solar system, its invisible nitrogen gas, providing the gentle thrust? The theories were as wild as the object itself. We had mere weeks to study it before it faded from view, its secrets intact, leaving us with a profound and unsettling silence. Oumuamua was a cosmic spectre, a ghostly courier that delivered a message we couldn't read, a question mark flung from the heart of the galaxy. It proved that the ocean between the stars was navigable, that visitors could and would arrive. We were no longer alone in that sense, but it left us wondering if we would ever truly understand them. For 2 years the silence held. The puzzle of Oumuamua deepened, becoming a modern myth in the scientific community. We waited, scanning the heavens with a newfound urgency, knowing that the first visitor was unlikely to be the last. Then, in August of 2019, the alert came again. An amateur astronomer in Crimea, Gennady Borisov, spotted a fuzzy object moving through the pre-dawn sky. Once again, the orbital calculations began, and once again, the result was an impossible hyperbola. It was happening again. The second messenger had arrived. Designated 2I, Borisov, this visitor, was immediately breathtakingly different from its predecessor. Where Oumuamua was a ghostly, inert enigma, Borisov was a glorious, spectacular comet. As it plunged toward our sun, it behaved exactly as a comet should. It lit up, growing a vast, glowing coma of gas and a magnificent tail of dust that stretched for millions of kilometers behind it. It was a sight both reassuringly familiar and deeply profound. Here was a classic comet, a dirty snowball from the outer reaches of a star system doing what comets do. But this one wasn't times ours asterisk. For the first time, we were looking at a pristine piece of another solar system, and it looked familiar. Its very existence confirmed a crucial hypothesis that the building blocks of solar systems, these icy relics, are likely common throughout the galaxy. Other stars build their families in much the same way ours did, but familiarity does not mean identity. As our instruments dissected the light from Borisov's coma, we found the unique chemical fingerprint of its birthplace. While it had water and other compounds common in our own comets, it also contained an astonishingly high concentration of carbon monoxide, far more than any comet from our own Oort cloud has ever displayed. This small chemical detail was a monumental clue. It suggested that Borisov was born in a much colder, more carbon monoxide-rich region of its home nebula than our own comets were. It likely formed in the orbit of a red dwarf star, the most common type of star in the Milky Way, a star very different from our own yellow Sunday. Borisov was our first tangible sample from an alien world. It wasn't a cryptic puzzle like Oumuamua. It was a geologic specimen, a Rosetta Stone, that allowed us to read the chemistry of a place we may never see. It told us that while the processes of planetary formation might be universal, the local conditions, the specific ingredients can vary dramatically from one star to another. The two visitors, 1I and 2I, painted a tantalizing but incomplete picture. One was a bizarre, unreadable spectre. The other, a familiar, yet chemically distinct cousin. One raised questions about the nature of objects in the void. The other gave us our first real data point on the chemistry of another star's family. They were the first 2 sentences in a book we were just learning to read, and now the third sentence is being written across our skies. This time it is different. This time we were not caught by surprise. We saw it coming from a long way off. It's called 3I, Atlas discovered by the Asteroid Terrestrial Impact Last Alert System. Like Borisov, it appears to be an active comet, a traveller shedding its ancient skin as it feels the warmth of our sun for the very first time. Its trajectory is another magnificent hyperbolic arc, a clear testament to its interstellar origins. We have had more time to prepare for this arrival than for any other. Our telescopes, our planetary radar systems, our space-based observatories are all being marshaled, turning their sophisticated gaze toward this incoming emissary. We have tracked its path with unprecedented precision, calculating not just where it has been, but exactly where it is going. And its destination, the point of its closest and most dramatic encounter with our world, is what makes this event a once-in-a-generation scientific opportunity. Because 3I, Atlas, is on a collision course, not with a planet but with a concept. It is headed directly for the ecliptic plane. To understand the monumental significance of this, you must picture our solar system not as a random scattering of worlds in space, but as a remarkably flat, orderly structure. Imagine the Sun at the center of a colossal spinning vinyl record. The planets from Mercury to Neptune all orbit within the grooves of this record, traveling on nearly the same geometric plane. This shared plane of existence, this grand celestial highway, is the ecliptic. It is the flattened disk of our cosmic family, the foundation upon which our entire system was built. It is the plane through which Earth travels on its annual journey around the Sunday. It is in essence the very floor of our home. Both Oumuamua and Borisov pass through our system on steeply inclined trajectories, like visitors swooping down from the high ceiling or up from the basement. Their paths cut through the ecliptic at a sharp angle, meaning they spent very little time within that bustling, data-rich environment where our best observatories live and work. Their passage through the plane was fleeting, a blink and you'll miss it moment. But 3I, Atlas, is doing something extraordinary. Its trajectory is aligned in such a way that it will cross the ecliptic plane at a shallow angle. It will not just pierce our system's primary disk, it will glide through it. This march, this interstellar wanderer, will perform a maneuver of profound astronomical importance. It will journey directly through the heart of our world, the very space we inhabit, giving us a prolonged front-row seat to its performance. For a precious window of time, it will be perfectly positioned for observation from both Earth's northern and southern hemispheres. It will be illuminated by the sun in a way that maximizes the light reflecting from its nucleus and its developing coma. This is the golden ticket for astronomers. The shallow crossing angle means we can bombard it with radar signals from Earth, hoping to map the surface of its nucleus and determine its shape and rotation, a feat we could only dream of with Oumuamua. The James Webb Space Telescope can stare into the heart of its gassy envelope, using its infrared vision to search for complex organic molecules, the very building blocks of life that may have formed around a star hundreds of light years away. Our ground-based spectrographs can dissect its light with unparalleled precision, teasing out the subtle chemical signatures that will tell us about the temperature, the pressure, and the elemental composition of its birthplace. This isn't just another flyby. This is a full-scale, coordinated global investigation. It's the equivalent of a mysterious ship from an uncharted land, not just sailing past our coast, but slowly navigating right through our main harbour under the full glare of our spotlights, allowing us to inspect its rigging, its cargo, and the strange flag it flies. This passage across the ecliptic is a celestial alignment that transforms a distant curiosity into an accessible laboratory. The key to unlocking the secrets of another star system is not just coming to us, it is presenting itself in the most ideal way imaginable. As 3I, Atlas, prepares for its March transit, a silent anticipation settles over the astronomical world. We are poised on the edge of a great revelation. The third messenger is here and it is ready to speak. The question that echoes in every control room and observatory dome across the planet is a simple one, yet it holds the weight of worlds. What is it about to tell us? It began not with a thunderous announcement, but with a whisper, a phantom signal in the digital ocean of the cosmos. On the volcanic slopes of Haleakala and Mauna Loa, robotic eyes open to the gathering dark sentinels in a silent, ceaseless watch. These are the telescopes of the Asteroid Terrestrial Impact Last Alert System, or ATLAS, our planet's dedicated guardians against cosmic intruders. Night after night, they perform a colossal Sisyphean task. They photograph the entire visible sky again and again, a relentless sweeping gaze that generates an unimaginable deluge of data. Millions of stars, galaxies, and nebulae are captured, their ancient light converted into cold, hard numbers. And somewhere buried within this storm of information, this blizzard of photons from every corner of the universe, a single fugitive point of light was beginning its betrayal. The system is designed for automation, for inhuman patience. Software, not a person, performs the first ritual of discovery. It compares tonight's sky with last night's, subtracting the static, unchanging backdrop of the distant universe. What remains are the movers, the wanderers, the restless nomads of our own solar system, the asteroids, the comets, the celestial flotsam and jetsam, and on a night like any other, the algorithm flagged a new one. A smudge of light barely brighter than the background noise, so faint it could have been a glitch, a cosmic ray striking a sensor. It was given a provisional designation, a sterile, anonymous name, but this smudge was different. It wasn't behaving like the others. It wasn't following the familiar, well-trodden paths of our system's inhabitants. Its movement was subtle, yet possessed a strange, inexorable quality. A ghost in the machine had been found. The initial detection was merely the sounding of a silent alarm, a single flare fired into the global darkness of astronomical research. The coordinates were automatically uploaded to the Minor Planet Center, the world's clearinghouse for all things that move in the night sky. And here the frantic human part of the story begins. A call went out across the planet, a digital plea echoing through observatories. Confirm this object, track it, give it a past so we can give it a future. From the arid deserts of Chile to the remote peaks of the Canary Islands, telescopes swiveled their great domes, rotating with a low hum, turning their massive mirrors toward a tiny, unassuming patch of sky. This is a race against time, a desperate chase where the quarry is millions of kilometers away, and the finish line is the horizon when the object sinks from view. The first few observations are everything. They are the anchor points from which an entire history can be extrapolated. Without them, the object is just a fleeting phantom lost again to the void. For days, the data trickled in a collection of disparate sightings from around the world. Each one was a single pinprick of light, a moment in time and space. Astronomers worked through their nights, fueled by caffeine and pure adrenaline, fitting these points together, trying to connect the dots. They were attempting to solve the most profound celestial puzzle. Where has this visitor been, and where is it going? The initial orbits they calculated were messy, uncertain, but as more observations poured in, a shape began to emerge from the mathematical noise. It was a shape that sent a jolt through the scientific community. Every object born within our solar system follows a predictable path, a closed loop governed by the sun's immense gravitational field. They travel on circles or more commonly elegant ellipses. Like a cosmic carousel, they are bound to the sun, destined to return again and again over millennia. Even the most eccentric comets, swinging out to the solar system's icy fringe, eventually feel the sun's gravitational leash and begin their long fall back home. Their orbits are a signature, a birth certificate that reads, "Property of the Sol System." This object, however, was drawing a different pattern against the stars. Its path was not a gentle returning curve. It was a dramatic sweeping arc, a shape known as a hyperbola. A hyperbola is not a loop. It is a path of escape. It is the trajectory of something moving so fast that a star's gravity cannot contain it. It is a one-way ticket through a solar system. This was not a member of our family. It was not a prodigal son returning from the cold depths. It was an intruder, a traveler from the interstellar deep. This was the cosmic fingerprint of an alien, a definitive mathematical proof that the faint smudge of light in their telescopes had not been born of our Sunday. It had come from another star. A star whose name we do not know, whose location is a mystery, a ghost sun somewhere in the vast, churning river of the Milky Way. The object was given its new permanent name, its interstellar passport, 3I, Atlas. The 3I standing for the third interstellar object ever confirmed by humanity. The discovery was electrifying, but it was only the beginning. Confirming its origin was one thing, understanding its destiny was another. Now the true work of the celestial cartographers began. With the hyperbolic nature of its trajectory, established supercomputers around the world were fed the stream of observational data. Their task was to chart its course through the intricate, invisible architecture of our solar system. You have to imagine the solar system not as an empty space with a few planets, but as a complex, dynamic web of gravitational currents and eddies. The Sun is the anchor, the great central vortex, but every planet exerts its own pull, a subtle but significant tug. As 3I, Atlas, plunged inward, its path would be gently bent and shaped by these forces. The immense gravity of Jupiter, the solar system's behemoth, would act like a giant lens refracting its trajectory. The elegant rings of Saturn, the distant twins of Uranus and Neptune, even the tiny nudge of sunlight itself, the pressure of photons striking its surface, all of these minute variables had to be accounted for. The calculations were of staggering complexity, a form of celestial prophecy written in the language of physics and differential equations. Thousands of simulations were run, each one a slightly different what-if scenario, honing the prediction, narrowing the cone of uncertainty until a final breathtaking path was resolved. And this path revealed something momentous, a destiny, an appointment. It showed that 3I, Atlas, was on a collision course not with a planet but with a concept, a flat geometric plane upon which our entire solar system is built. The ecliptic. Imagine our solar system as a vast spinning record. The Sun sits at the center, and all the planets orbit in the grooves on its surface. This flat surface, this cosmic vinyl, is the ecliptic plane. It is the main street of our solar system, the grand stage where all the primary action happens. Our interstellar visitor was not approaching along this plane. It was diving in from above, from the galactic north, plunging down at a steep, dramatic angle. And the calculations, now refined to an astonishing degree of precision, all pointed to a single critical event. In March, 3I, Atlas would pierce the veil. It would cross the ecliptic plane. This was not just a geometric curiosity. It represented a moment of profound scientific opportunity. At that point of intersection, the object would be at its closest and most active, its trajectory perfectly positioned for our Earth-based and spaceborne observatories. It would be a scheduled rendezvous between humanity and a messenger from another star system, a moment when the secrets it carried might finally be coaxed into the light. This wasn't our first encounter with such a spectre. We had been haunted by these visitors before. Our understanding of 3I, Atlas, is built upon the ghosts of its predecessors. First, there was Oumuamua in 2017. The name is Hawaiian for scout, and it was a fitting one. It was the very first, a complete and utter enigma. Oumuamua was a dark, reddish, cigar-shaped object tumbling end over end as it sped through our system. It showed no signs of being a comet. There was no fuzzy coma, no majestic tail. It looked like a dry, inert piece of rock, but something was pushing it. As it swung past the Sun, it accelerated away faster than gravity alone could explain. It was a mystery that baffled scientists and ignited wild speculation. What was this non-gravitational acceleration? Was it outgassing of materials we couldn't see? Was its strange shape catching the solar wind like a sail? Oumuamua was a maddening puzzle. It gave us our first taste of the interstellar unknown, but it was discovered late, already on its way out. It was a fleeting glimpse, a cosmic question mark that shot past us and vanished back into the dark, leaving us with a profound sense of a missed opportunity. Then just 2 years later came 2I, Borisov. If Oumuamua was the strange, unnerving alien, Borisov was the familiar cousin from a distant land. Discovered by an amateur astronomer, Gennady Borisov, it looked and acted exactly like a comet from our own Oort cloud. It had a brilliant dusty coma and a long, graceful tail of gas. Spectroscopy revealed it was shedding water vapor just like our comets. It was a comfort, a confirmation. Borisov proved that other star systems create comets just like ours. It told us that the fundamental building blocks of planets and life, the water and organic compounds locked away in comets, are likely common throughout the galaxy. Borisov grounded us. It gave us a baseline. It demonstrated that at least some interstellar visitors would be reassuringly familiar. It was a crucial piece of the puzzle, a scientific touchstone. But it too was a difficult object to study in exhaustive detail. Oumuamua was the shock. Borisov was the confirmation. And now there is 3i, Atlas. It represents something new. It represents a third way. It represents readiness. We are no longer unprepared. The lessons learned from the frantic chase of its two predecessors have been codified into a global rapid response strategy. We detected 3i, Atlas, early on its way in, giving us months, not weeks, to prepare. We now have a worldwide network of telescopes, including the powerful James Webb Space Telescope, all primed and ready, their observation schedules cleared for the critical moment. Unlike the enigmatic Oumuamua 3i, Atlas appears to be a comet, showing early signs of activity that promise a spectacular show, a trove of data to be sifted and analyzed. And unlike Borisov, its trajectory offers us a front-row seat, a scheduled performance right on the main stage of our solar system. This object is not just another data point. It is a time capsule. It is a pristine, frozen fragment from the birth of another solar system, a place that may have formed billions of years ago under conditions completely alien to our own. It carries within its icy heart the chemical signature of its home star, the raw ingredients of its long-dead protoplanetary disk. It is a physical piece of another world delivered to our doorstep. The scout taught us to be vigilant. The familiar cousin taught us what to expect. Now the third messenger has arrived, and its impending passage across the ecliptic plane in March is not merely an astronomical event, it is the culmination of decades of searching a focal point for our insatiable curiosity. It is our chance to finally reach out and touch the ghost, to ask the questions that have haunted us since we first looked up and realized that the stars were other suns. What secrets are locked in its ancient ice? What story does it have to tell about the place it once called home? And as it cuts across that fundamental plane of our existence, will it bring us answers, or will it only deepen the magnificent, terrifying mystery of our place in the cosmos? The appointment is set. The world's eyes are turning toward this celestial fugitive, and the clock is ticking. The deep quiet that followed its discovery was fleeting. It was the calm before a storm of intellectual energy, a global intake of breath before the plunge. For as the Earth continued its silent, patient lap around the Sun, the calendar pages turned inexorably toward March. The approach of 3i, Atlas, was no longer a distant astronomical curiosity. It had become a deadline. A whisper in the deep space tracking networks had amplified into a worldwide roar of preparation, a mobilization of human ingenuity on a scale reserved for only the most profound cosmic appointments. Across the planet, in the hushed domes of mountaintop observatories and the humming clean rooms of space agencies, a singular focus began to crystallize. The visitor was coming, and humanity was preparing its welcome. This was not simply a matter of pointing our telescopes in the right direction. It was a coordinated, intricate dance of physics, engineering, and sheer human will. In mission control rooms, from Pasadena to Darmstadt, existing flight plans for billion-dollar spacecraft were scrutinized, debated, and painstakingly altered. A probe studying solar winds might be commanded to turn its sensitive particle detectors just for a few precious hours toward the faint whisper of gas trailing the interstellar interloper. Satellites designed to map our own world's weather patterns would be tasked with glancing outward, hoping to catch a stray photon from this ghost from another star. The great spaceborne observatories, our steadfast eyes in the void, saw their meticulously planned schedules thrown into a state of dynamic flux. Peer-reviewed proposals years in the making were respectfully postponed. The study of a distant galaxy, the characterization of a known exoplanet, these could wait. 3i, Atlas, could not. Its passage was a fleeting spectacle, a once-in-a-civilization opportunity that would not be missed. The stakes were simply too high. On the ground, the colossal sentinels of the night began their slow, deliberate pivot. In the bone-dry air of the Atacama Desert, the 4 monolithic units of the Very Large Telescope, each mirror the size of a small building, began the calibration sequences that would align their combined power on a single infinitesimally small point of light. In Hawaii, atop the sacred peak of Mauna Kea, the twin Keck telescopes, those grand pioneers of modern astronomy, were being fitted with instruments honed for this very moment. Engineers and technicians worked through the nights, their headlamps casting lonely pools of light in the freezing thin air, ensuring every spectrograph was perfectly tuned, every adaptive optics system ready to wage its nightly war against the blurring distortion of our own atmosphere. All over the world, this scene was repeated. A global network of steel and glass, a planetary-scale sensory organ was being awakened, and aimed not at a familiar neighbour but at a complete and utter stranger. The reason for this unprecedented frenzied focus was a matter of celestial geometry, an intersection of profound significance. Every planet, moon and asteroid born of our Sun orbits on or very near a single vast flat disk. This is the ecliptic plane. You can imagine it as a cosmic sheet of glass, an immense spinning record upon which all the worlds we know are etched into their gravitational grooves. It is the grand highway of our solar system, a bustling, crowded metropolis of rock and ice and gas, all held in thrall by the Sun's immense gravitational authority. It is the plane of our origin, the disk from which Earth itself coalesced. And because of this, it is also a wall of noise, a curtain of light and dust. When we look out from our home, we are almost always looking through this crowded plane. Our view is forever contaminated by the zodiacal light, that faint ethereal glow of countless dust particles shed by comets and asteroids over billions of years, all trapped within the plane. It's like trying to watch a distant firefly through a swirling blizzard. But 3i, Atlas, was not from here. It was not bound by the rules of our provincial neighbourhood. Its trajectory was a defiant slash of chalk across the blackboard of our solar system, approaching from a steep, almost perpendicular angle. It was a submarine surfacing from the deep, dark, silent waters far below the chaotic surface of the ecliptic. And in March, for a few glorious, scientifically priceless weeks, it would breach that surface. It would cross the ecliptic plane, rising above the cosmic fog, offering us a perfectly clear, unobstructed view. This moment, this specific crossing, was the scientific equivalent of a total solar eclipse, a transit of Venus, and the closest approach of a comet, all rolled into one ephemeral event. It was a chance to study an object from another star system with a clarity we had never before thought possible. The obscuring dust, the glare of nearby asteroids, the entire glittering chaos of our own home would be for a short while beneath it. We would see it as it truly was, stripped bare against the clean black velvet of deep space. This fleeting window of clarity dictated the entire strategy of the observation campaign. It was a multi-pronged assault on the unknown, designed to wring every possible secret from the comet in the short time available. The first line of attack would come from the ground-based giants, their primary weapon spectroscopy. As 3i, Atlas, drew closer, sunlight would warm its surface, causing its primordial ices to sublimate directly into gas. This process would create a tenuous atmosphere, a coma, and a tail of dust and vapor. By capturing the faint light passing through this coma and splitting it with exquisitely precise prisms, astronomers could read its chemical fingerprint. Every element, every molecule absorbs and emits light at very specific frequencies, creating a unique spectral barcode. Was the water ice in this comet the same as ours, with the same ratio of hydrogen to its heavier isotope deuterium? This single measurement could rewrite our understanding of how Earth got its oceans. Did its spectrum show the signatures of complex organic molecules, the building blocks of life formed in the protoplanetary disk of a completely alien star? Finding them would be a monumental discovery, suggesting that the ingredients for life are not unique to our little corner of the cosmos. These great telescopes would act as cosmic chemists, performing a remote analysis of a substance forged in a crucible light years away and billions of years in the past. Simultaneously, another set of instruments would be trained on the visitor polarimeters. These devices measure the orientation of light waves. When sunlight bounces off the tiny dust grains in a comet's tail, its light becomes polarized. By analyzing the angle and degree of this polarization, scientists can deduce the physical properties of the dust itself. Are the grains fluffy and porous like snowflakes, or are they dense and compact like grains of sand? Are they carbon-rich and dark, or silicate-rich and bright? This isn't merely a geological curiosity. The structure of these dust grains tells a story. It speaks of the conditions in the interstellar cloud where 3i, Atlas, was born, revealing the pressures, temperatures, and dynamics of a stellar nursery we will never see directly. It would be like a paleontologist reconstructing an entire ecosystem from a single fossilized bone. We would be touching the texture of another solar system's raw material, feeling its primordial grit between our fingertips from a distance of millions of miles. While the Earthbound observatories waged their nightly battle with the atmosphere, our champions in orbit prepared for their own unique roles. The Hubble Space Telescope, that venerable and tireless eye in the sky, would provide the sharpest possible images in visible and ultraviolet light. Free from atmospheric blur, Hubble could resolve the structure of the inner coma with breathtaking clarity, watching for the sudden jets and outbursts of gas that betray the active vents on the nucleus's surface. It would create a time-lapse movie of a rotating interstellar iceberg, mapping its features as it tumbled through space. Its ultraviolet sensors, meanwhile, were crucial for tracking the cloud of hydrogen, invisible to our eyes, that would bloom around the comet as solar radiation broke down its water molecules. The sheer size of this hydrogen halo would give us a direct measure of how much water the comet was losing each second, a vital clue to its overall size and composition. Yet it was the newest jewel in our orbital crown, the James Webb Space Telescope, that held the promise of the most profound revelations. Webb sees the universe not in the visible light our eyes are attuned to, but in the ethereal realm of the infrared. For Webb, looking at 3i, Atlas was like putting on a pair of thermal goggles. It could bypass the scattered sunlight that dazzles other telescopes and see the comet's own intrinsic heat, the faint glow of a body warmed by a distant sunday. This infrared vision would allow it to perform a different kind of spectroscopy, one sensitive to the specific vibrational signatures of ices. While ground telescopes could spot the gaseous products of sublimation, Webb could see the ices themselves times before times they turned to gas. It could directly identify frozen carbon dioxide, methane, ammonia, and carbon monoxide locked within the nucleus. This was the Holy Grail, a direct inventory of the pristine primordial deep freeze from another star. It was the equivalent of drilling an ice core, not into an Antarctic glacier, but into a relic from a world that may no longer even exist. And then there were the ears. Far from the optical domes, vast arrays of radio telescopes, like the Atacama Large Millimeter, Submillimeter Array ALMA, would also turn to listen. These networks of dishes don't see starlight. They detect the faint, low-energy radiation emitted by cold molecules spinning in space. Has the sun warmed 3i Atlas molecules, like hydrogen, cyanide, and formaldehyde, crucial precursors to amino acids, would be released into the coma. In the cold vacuum, these molecules would emit a faint radio whisper at very specific frequencies. ALMA, by combining the signals from dozens of antennas, could not only detect this whisper, but could also map its location, tracking how these complex organic materials spewed from the nucleus and evolved in the solar wind. We wouldn't just be taking a chemical inventory, we would be watching the process of prebiotic chemistry unfold in real time, driven by the engine of an alien sun. Coordinating this global orchestra of glass, steel, and silicon was a monumental undertaking. It required a symphony of communication across dozens of institutions and 24 time zones. A central clearinghouse, a consortium of astronomers worked around the clock, refining the visitor's trajectory with every new observation. The slightest deviation in its predicted path could mean a multi-billion-dollar observatory would be staring at empty space. Supercomputers churned through terabytes of tracking data, modeling the subtle non-gravitational forces acting on the comet. The gentle push of its own outgassing, a force as delicate as a human breath, was enough to nudge its path over astronomical distances, and these nudges had to be calculated with near-perfect precision. A complex interlocking schedule was devised, a celestial timeshare agreement, ensuring that as one telescope set below the horizon in Chile, another was rising in Hawaii to pick up the watch. When Webb needed to perform a long-duration stare, other observatories would focus on monitoring the comet for sudden outbursts that could inform Webb's own pointing and exposure times. Data sharing agreements, normally tangled in academic bureaucracy, were streamlined. There was no time for competition, only collaboration. The entire astronomical community was acting as a single global intelligence. its senses scattered across the planet and its near-space environment, all unified by a single burning question: what are you? The plans were laid. The instruments were calibrated. The teams were in place. A tangible tension began to fill the air in control rooms and university halls, a mixture of profound excitement and deep anxiety. They had one shot. The crossing of the ecliptic plane would last only a few weeks. The period of optimal pristine viewing would be shorter still. An unexpected solar flare could disrupt communications. A critical instrument could fail. The comet itself, a notoriously unpredictable beast, could suddenly disintegrate under the sun's tidal stress and thermal shock, shattering into a cloud of unremarkable dust before it ever gave up its most precious secrets. All of this immense effort, this colossal mobilization of our species' scientific might, was balanced on the knife edge of chance. As February gave way to the first days of March, a collective breath was held. The final approach had begun. The silent visitor from the stars was about to pass directly through the heart of our home, and every eye we possessed was turning to watch. Undefined. For weeks, the narrative had been one of anticipation, a story written in the future tense, composed of orbital mechanics and elegant yet sterile predictions. We had traced its path from the cold interstellar dark, followed its silent arc through the lonely outer provinces of our sun's domain, and waited. Now the waiting was over. The models had run their course, the theories had been debated to exhaustion, and all that remained was the quiet, profound act of observation. Across the planet, a coordinated network of humanity's greatest eyes, from the high, dry deserts of Chile to the volcanic peaks of Hawaii, swiveled in unison, a silent mechanical ballet directed by a single incoming truth. They were all aimed at an invisible line in space, a geometric boundary of immense significance, the very disk upon which our own world spins. The final countdown wasn't measured in the booming voice of a mission controller, but in the silent, relentless ticking of celestial clocks in the final few million kilometers of an unimaginable journey. The air in control rooms wasn't thick with rocket fuel, but with the palpable tension of imminent discovery. The moment was at hand. 3i, Atlas, the ghost from another star, was about to step onto our stage. Through the digital eye of our most powerful simulations, you can see the solar system not as a collection of worlds, but as a vast, shimmering record player. The planets, our familiar homes and neighbors, are etched into grooves of gravitational certainty, all spinning on a single, astonishingly flat plane. This is the Ecliptic. It is the grand thoroughfare of our solar system, the level ground upon which everything we know was built. For an object born here, navigating this plane is second nature. But 3i, Atlas, was not from here. It was a trespasser, an entity from the wild country beyond our borders, and its trajectory was an act of violation, a steep, piercing dive. Our simulations show it approaching not from the side, but from a high oblique angle, plunging down towards this bustling cosmic highway. The ecliptic isn't empty space. It's a region of higher density, a swirling river of dust, shed by comets of asteroids, ground to powder over eons, and of a more concentrated, more violent solar wind, a stream of charged particles blasted from our star. For 3i, Atlas, this crossing was not a gentle merger with traffic. It was a violent submersion, a shock to its ancient and frigid system. The visualization transforms into a cross-section, the ecliptic plane, now a brilliant, incandescent line of light. We see the object, a dark point of condensed starlight, accelerating as it falls into the sun's deepening gravity well. Its own wispy, ethereal coma, the cloud of gas and dust sublimating from its surface, which had been its constant companion in the void, now begins to visibly interact with this new, harsher environment. Streams of solar plasma, magnetic field lines made visible, wrap around the visitor, contorting its atmosphere. It's like watching a deep-sea submersible descend past the sunlit zone into the crushing alien pressures of the abyss. Every particle of dust in the ecliptic it strikes, even those no larger than a grain of sand, hits with the force of a tiny explosion, a microscopic flash of kinetic energy converted into heat and light. The sun, no longer a distant placid star, has become a celestial blowtorch, its radiation pressure pushing, scouring, and sculpting the object's every feature. The crossing itself, the precise mathematical moment its center of mass intersects that geometric plane, is instantaneous, a silent, unceremonious event in the grand emptiness. But its consequences, the physical repercussions of this violent transition, would ripple outwards at the speed of light, carrying with them the first true secrets of this interstellar wanderer. Back on Earth, there is nothing to see yet. Even as the object completed its crossing the light from that event, the very first photons bearing witness to the encounter had only just begun their own journey across the void. They were racing towards us at the absolute speed limit of the universe, but space is vast, and the gap between our world and that precise point in the cosmos was immense. For over 8 minutes, the truth of what had happened hung in transit, a message sealed in an envelope of light streaking across 150 million kilometers of vacuum. In those agonizing minutes of silence, astronomers could only do one thing: trust their instruments. They checked calibrations, monitored atmospheric conditions, and stared at screens that still showed the object as it was 8 minutes ago on its final approach. It's a fundamental reality of our place in the universe, a constant reminder of our isolation. We are always inescapably looking into the past. Every discovery is an act of archaeology, of unearthing a reality that has already transpired. The scientists in those rooms were waiting for a ghost to arrive, a phantom image of a moment that was already history millions of kilometers away. Then it came, not as a sudden flash or a dramatic explosion, but as a quiet, relentless cascade of data. On a screen in the Paranal Observatory in Chile, a raw image from the Very Large Telescope's array resolved itself. It was a monochrome collection of pixels, a spray of white dots against a black background, utterly devoid of romance to the untrained eye. But to the astronomers gathered there, it was the most beautiful thing in the world. This was the first light from the other side. Within seconds, a torrent of information followed, flowing through fiber optic cables to data centers around the globe. Numbers, spectral lines, photometric readings, the cold, hard language of the cosmos. Teams of researchers who had rehearsed this moment for months now sprang into action. Algorithms began to churn, processing the raw data, filtering out the noise of Earth's atmosphere, subtracting the light of background stars, and slowly, painstakingly building a clear portrait of 3I Atlas in the immediate aftermath, its critical passage. The virtual silence was broken by the frantic clatter of keyboards and the low murmur of scientists speaking in the rapid coded language of their field. The hunt was on. The very first processed image that solidified on the main display silenced the room. Everyone had a clear, model-driven expectation of what they would see. A cometary coma, the fuzzy ball of gas and dust surrounding the nucleus, should have been slightly brighter, perhaps a little more elongated due to the increased solar pressure. The reality was profoundly different and immediately unsettlingly wrong. The coma wasn't just brighter, it was incandescent, glowing with an intensity that defied all predictions. Models based on its behavior in the outer solar system had calculated a specific rate of sublimation, a predictable amount of gas that should be boiling off its surface. What they were seeing was an object that was, for its size and distance, impossibly luminous. It blazed in the dark, not like a dusty snowball catching the sun's light, but like something that was generating its own. And the shape was bizarre. Instead of a roughly spherical or teardrop-shaped halo, the coma possessed a strange, almost geometric structure. There were distinct layers, concentric shells of gas that pulsed with a soft ethereal light like ripples on a ghostly pond. It was organized, it was structured, and in the cold, chaotic physics of cometary decay, structure of this kind was not supposed to exist. It was as if they were looking not at a simple, inert block of ice and rock, but at a far more complex system, an engine of unknown design. While the imaging teams were grappling with the coma's shocking appearance, another group was staring in disbelief at their own screens. These were the spectroscopists, the scientists who dissect light itself, breaking it down into its constituent colors to read the chemical fingerprints of distant objects. Their instruments had been gathering the photons from the coma and passing them through prisms and diffraction gratings, creating a rainbow spectrum riddled with dark and bright lines. These lines are the barcodes of the elements. Each element, each molecule absorbs and emits light at very specific, unchangeable frequencies. The pre-crossing spectrum of 3I, Atlas, had been faint but predictable, showing the familiar signatures of water ice, carbon monoxide, and silicates, the standard building blocks of comets throughout our own solar system. The new spectrum, the first analysis of the gas being violently stripped from it times after times crossing the ecliptic, told a profoundly different story. The familiar lines were there, yes, but they were drowned out by a series of powerful, brilliantly sharp emission lines that corresponded to nothing they had expected. There was an astonishingly high abundance of xenon, one of the rarest and heaviest noble gases, which is almost never seen in such concentrations in comets. Its presence hinted at an origin in a truly exotic environment, perhaps the outer layers of a dying star far more massive than our own. Stranger still was a series of spectral lines that the analysis software couldn't immediately identify. After cross-referencing every known atomic and molecular database, the team isolated the signal. It was the distinct signature of complex hydrocarbons, but with an unusual isotopic ratio. The carbon atoms within these molecules, the very backbone of organic chemistry, contained a higher than normal proportion of carbon-13, a heavier, stable isotope of carbon. In our solar system, the ratio of carbon-12 to carbon-13 is remarkably consistent, a foundational measure of our cosmic neighborhood. The material boiling off 3I, Atlas, was fundamentally isotopically alien. It was a chemical dialect from another corner of the galaxy, a message written in an alphabet we were only just beginning to decipher. The object wasn't just a visitor, it was an emissary carrying a sample of a chemistry utterly foreign to our own. But the most profound mystery was yet to emerge. It came not from a single image or a spectrum, but from a simple graph, a plot of brightness against time known as a light curve. For any rotating, irregularly shaped object like a comet nucleus, the light curve should show a smooth, predictable wave as different faces of the object turn to reflect sunlight towards us. Its period tells you the object's rotation speed its day. The team monitoring the photometry of 3I, Atlas, had been tracking this for hours, expecting to pin down its rotation. What they found instead would change the entire nature of the investigation. The object's brightness wasn't just varying smoothly, it was pulsing. Superimposed on the gentle rolling wave of its rotation was a rapid, subtle, but undeniably regular flicker. It was a rhythmic beat, a metronomic pulse of light occurring every 4.72 seconds. It was too fast for rotation. It was too regular for any known natural process of outgassing which happens in chaotic, unpredictable jets. The first assumption was an error, a glitch in the instrument, a flaw in the detectors. A frantic series of communications flashed across the globe. Independent observatories in Arizona, in Spain, in South Africa were urged to check their own photometric data. The replies came back one by one, each confirming the unbelievable. They all saw it. The pulse was real. It was intrinsic to the object itself. 3I Atlas was throbbing with a soft rhythmic light, a cosmic heartbeat in the dark. A natural object, a simple piece of interstellar debris, does not do this. Natural processes are messy, chaotic, governed by the elegant but impersonal laws of physics. Regularity, especially on such a rapid and precise timescale, implies a mechanism. It suggests a process that is regulated, controlled, or the product of a highly ordered internal structure. In that moment, in control rooms filled with the quiet glow of computer screens, the entire perception of 3I Atlas shifted. The conversation was no longer about a comet. It was no longer a simple question of geology or chemistry. The object had ceased to be a passive, inert traveler and had become an active, dynamic enigma. The initial elation of a successful observation, the thrill of seeing a prediction come to pass, had evaporated. It was replaced by a far more potent and humbling emotion, profound, bottomless confusion. The elegant models were broken. The neat boxes of categorization had been shattered. Every piece of new data that arrived wasn't answering questions, but was instead screaming 1,000 new ones. What complex process inside this object could generate such a structured, multi-layered coma, defying the simple physics of sublimation? From what bizarre stellar nursery could it have acquired such an exotic, alien-heavy chemistry, a fingerprint so unlike our own? And the pulse. What conceivable natural engine could cause an object of its size to flicker with the precision of a celestial clock? This was no longer just an interstellar comet. That label felt woefully inadequate, a relic of a simpler time just a few hours ago. We had reached out to study a piece of debris from another star, hoping to learn about the formation of other solar systems, but what we found was something that challenged our understanding of what an object adrift in the interstellar void could even be. The crossing of the ecliptic, once seen as the climax of our story, was now clearly just the beginning. The visitor had not only entered our home, it had just revealed its true incomprehensible nature, and in the breathless vacuum of space, the moment passed. 3I, Atlas, our fleeting guest from another star, had done it. It had sliced through the bustling, chaotic plane of our solar system, the cosmic freeway where all our planets orbit, and emerged on the other side. For a handful of excruciating minutes, there was nothing. Only the faint, expectant hum of servers in darkened control rooms across the globe. The worldwide network of telescopes from the high, dry deserts of Chile to the orbital platforms soaring above the atmosphere had tracked it, held it in their unblinking gaze through the passage. And now they listened. They waited for the torrent of photons, the whisper of data that had travelled for hundreds of millions of kilometres, to finally arrive and tell us what had happened. It was a silence filled with a billion unspoken questions, a collective holding of breath by an entire species. Had it survived the gravitational crosscurrents? Did the sudden spike in solar radiation trigger something new? We had sent our most sophisticated questions into the void, and now we simply had to wait for the universe to answer. Then the dam broke. Not with a roar, but with a tsunami of light and information. Petabytes of raw data flooded the servers, a digital avalanche cascading into processing centers from Hawaii to the Canary Islands. It was a scientific gold rush in real time. Automated software pipelines, honed over years for this very encounter, began the colossal task of cleaning, calibrating, and converting the raw signals into something a human mind could comprehend. The first images, ghostly and streaked from the object's velocity, were stitched together. The first spectral readings, jagged lines of light and darkness, began to resolve on screens. In labs and university offices, coffee went cold in forgotten mugs. The world outside these rooms faded away. There was only the data stream, a direct line to an artifact from another sun, and the frantic, exhilarating scramble to be the first to understand its secrets. It was a moment of pure discovery, the kind of moment that scientists dedicate their entire lives to experiencing just once. Every pixel, every wavelength, every subtle fluctuation was a new word in a language we had never heard before, a sentence in a story that began in a place we may never see. The very first surprise, the one that sent the initial shockwave through the assembled teams, was not a grand explosive revelation. It was a whisper, a ghost in the machine. It came from the spectrograph's instruments that act as cosmic prisms, breaking down the faint light, reflecting off 3I, Atlas, into its constituent chemical fingerprints. We expected to see the familiar signatures of water ice, of carbon compounds, the building blocks of comets we have known our entire existence. And they were there, faint but undeniable. But nestled among them, there was something else, or rather a profound lack of something. The element argon, a noble gas, was almost completely absent. In our own solar system, the ratio of argon to water in comets is a fundamental yardstick. It tells us about the temperature and pressure in the primordial nebula where these objects were born, a kind of cosmic birth certificate. Argon freezes at extremely low temperatures, so its presence is a signpost of formation in the frigid outer reaches. To find an object with water ice, but virtually no argon, was like finding a polar bear in the Sahara. It made no sense. It was a contradiction in terms of violation of the established rules of planetary formation as we understood them. The initial reaction was disbelief, a frantic search for instrumental error or miscalibration, but the signal was confirmed independently by 3 different observatories. The ghost was real. This object did not come from a place like the protoplanetary disk that formed our own sun. The implications were staggering. Was its parent star unusually hot, burning away the argon before it could ever freeze onto the nascent planetesimals? Or was it formed in a region of its nebula with a bizarrely different chemical composition? The debate erupted instantly. spreading through encrypted chat channels and urgent video calls. Some theorists proposed it was born in the turbulent radiation-blasted inner circle of a young, violent star. Others argued for a more exotic origin, suggesting it could be a fragment from a world that had been torn apart, its lighter elements stripped away in some ancient catastrophe. The absence of a single element had suddenly thrown a wrench into every model we had. 3I Atlas wasn't just a tourist, it was a paradox, a piece of a puzzle that didn't seem to fit into any picture of the universe we had ever drawn. It was as if we had found a message in a bottle washed up on the shore, only to discover it was written in an alphabet with missing letters. While the chemists and geologists grappled with this compositional enigma, another team was staring mesmerized at a different kind of data. They were watching the object's light curve, the subtle rhythmic pulse of its brightness. For any rotating, irregularly shaped body, this curve acts like a heartbeat. As different facets of the object turn to face us, they reflect more or less sunlight, causing its brightness to rise and fall in a predictable pattern. By timing this celestial metronome, we can determine its rotation period, its day. The first few hours of data seem to confirm our predictions. The light from 3I Atlas was pulsing with a steady, stable rhythm, suggesting a rotation period of just over 9 hours. It was a solid, reassuring piece of data in a sea of growing confusion. It was tumbling through space in an orderly, predictable way. It was a rock. A very strange rock, but a rock nonetheless. The team began drafting a preliminary report, a small island of certainty. But as more data accumulated, the rhythm began to falter. The steady 9-hour heartbeat started to stutter. At first it was a minor blip, an anomaly that could be dismissed as instrumental noise. Then it happened again. The peak brightness would arrive a few minutes late. The dip wouldn't be quite as deep as the last. The clean, simple sine wave that had been building on their screens began to grow complex, overlaid with a second, much faster, much fainter rhythm. It was a chaotic, almost biological signal. The object wasn't just spinning. It was wobbling. It was precessing like a dying top, its axis of rotation tracing a slow, lazy circle against the stars. But even that didn't fully explain the high-frequency chatter in the signal. The team leader, a veteran of a dozen comet-chasing campaigns, stared at the screen, her mind racing through the possibilities. An object with such a complex tumble would be inherently unstable. It should have settled into a simple rotation billions of years ago. Unless something was actively disturbing it. The most radical and most tantalizing explanation was proposed in a hushed conference call in the early hours of the morning. 3I Atlas might not be a single object at all. It could be two. A binary system, a pair of interstellar voyagers locked in a tight, chaotic gravitational embrace. Two bodies orbiting a common center of mass, each tumbling and spinning in a complex dance that had been playing out for eons as they drifted through the interstellar dark. This contact binary or close-orbiting pair model would perfectly explain the bizarre, multi-layered light curve. The main 9-hour pulse would be the orbit of the two objects around each other, while the faster, fainter signals would be the individual rotations of each component. The theory was electrifying. We had never directly observed an interstellar binary object. This would be a completely new class of celestial body. It raised a host of new questions. How could such a delicate partnership survive the gravitational disruption of its ejection from its home star system? And how would it survive its perilous journey through our own? The simple, tumbling rock had transformed into a complex gravitational engine, a cosmic gyroscope whose intricate motions were a Rosetta Stone for the physics of a system we couldn't even imagine. The debate shifted from a simple question of rotation to a far more profound one about its fundamental nature and history. Yet the deepest mystery was still to come. It emerged from the thermal imaging cameras and the radio telescopes, the instruments designed to look not just at the object, but at the space immediately surrounding it. We were searching for a coma, the faint, glowing atmosphere of gas and dust that should be erupting from its surface as it warmed in the glare of our sun. Before the ecliptic crossing 3I, Atlas had been disappointingly inert, a silent, frozen traveller. Our models predicted that the increased solar radiation during its passage through the plane, the densest region of interplanetary dust and solar wind, would finally be enough to kickstart the process. We expected to see the telltale spectral lines of sublimating water ice, the blossoming of a pale ghostly tale. We aimed our instruments ready to witness the awakening of a primordial giant. What we saw was far stranger. There was activity, yes. A faint, tenuous cloud was indeed beginning to envelop the object. The radio antennae picked up the faint hiss of hydroxyl molecules, the broken-down remnants of water. But the amount was minuscule, a mere trickle compared to the flood we had anticipated. For an object of its size at this proximity to the sun, it should have been roaring to life like a celestial blowtorch. Instead, it was whispering. It was as if it were actively resisting the sun's heat, its surface bound together by some unknown, incredibly resilient material. But the true enigma was not what was present, but what else was there alongside the water. The mass spectrometers detected faint but unmistakable traces of molecular nitrogen and carbon monoxide gases that are far more volatile than water. They vaporize at much colder temperatures, typically in the distant frozen realms beyond Saturn. To find them actively venting this close to the sun was like finding a patch of frost on a hot stovetop. This phenomenon, which some began to call cold fire, was a complete subversion of cometary science. In our solar system, this kind of activity happens far from the sun. As a comet approaches, the nitrogen and carbon monoxide burn off first, and then as it gets hotter, the water ice takes over. 3I, Atlas, was doing both at once, but in the wrong place and in the wrong proportions. It was outgassing supervolatiles in a region of space where they should have all boiled away long ago. This suggested that the gases were not just on the surface, but were being actively supplied from deep within, its interior erupting through fissures in a thick, insulating crust. The object wasn't just a passive block of ice and rock. It was a dynamic, active world with its own internal geology, its own cryptic metabolism. It possessed a structure fundamentally different from any comet we had ever encountered. It was as if its heart was frozen, but its veins were flowing with a cryogenic lifeblood, venting the memory of its frigid birthplace into the warmth of our inner solar system. Within 72 hours of the ecliptic crossing, the scientific community was in a state of controlled chaos. The initial thrill of discovery had given way to the fierce, passionate friction of competing ideas. The data was so strange, so contradictory, that it could support multiple mutually exclusive interpretations. On one side, you had the fragment camp who argued that 3I, Atlas, was a shard of a larger differentiated body, perhaps a dwarf planet shattered in its youth. This would explain the strange chemical ratios and the potential for a dense insulating crust. On another side, the primordial camp insisted it was a pristine, unaltered relic from a uniquely cold and argon-poor region of an alien nebula, and that its binary nature was a key to understanding how such objects form. A third, smaller group, the exotics, quietly began to wonder if we were looking at something else entirely, something that wasn't formed through familiar gravitational accretion at all. Preprint servers, the digital battlegrounds of modern science, were flooded with papers. Titles were bold, abstracts were confident, but the content was pure high-stakes speculation, a furious attempt to build a new framework around a single uncooperative data point. The arguments were not just academic, they were deeply personal, pitting friend against friend, mentor against student. A team in Germany running massive computer simulations claimed that a binary object could not possibly have survived the journey. Therefore, the complex light curve had to be caused by massive asymmetrical outgassing jets, kicking the object into a chaotic tumble. A rival team in California countered within hours, presenting a model that showed how a specific kind of binary one that had kissed and fused slightly could be incredibly stable, and that the outgassing was far too weak to account for the observed wobble. We were watching the scientific method at its most raw and most human. It was a process driven not by cold logic alone, but by intuition, by ambition, and by the sheer unadulterated passion to be the one who finally solves the puzzle. We had come to 3I, Atlas, seeking answers about other worlds, but it had instead held up a mirror, forcing us to confront the limits of our own knowledge, the fragility of our most cherished theories. Every new packet of data only seemed to deepen the schism. The object was a cosmic Rorschach test. What you saw depended entirely on what you were prepared to believe. The missing argon, the stuttering heartbeat, the cold fire of its jets, these were not just isolated curiosities. They were interconnected clues in a mystery that was growing more complex with every passing hour. They painted a portrait of an object that was geologically active, structurally bizarre, and chemically alien. It was behaving by a set of rules we had not yet learned. The initial scramble for data was over. Now a new, more desperate race had begun, the race for comprehension. We had a fleeting window, perhaps only a few more months, to study this visitor before it accelerated back out into the interstellar abyss, taking its secrets with it forever. The first wave of discovery had washed over us, but it hadn't illuminated the shore. It had simply revealed how vast and dark the ocean of our ignorance truly is. And, as 3I, Atlas, continued its silent journey away from our sun, it left us with a new, more urgent, and far more unsettling question. If this is what one random visitor from the darkness looks like, what else is out there? What other impossibilities are currently hurtling through the void, waiting for their chance to cross our path and challenge everything we think we know? And so the paradox of 3I, Atlas, held the astronomical world in a state of suspended animation. The data streams from every corner of the Earth and from the cold silence of space painted a portrait of an object at war with itself. A ghost that possessed a solid shadow, a comet without a true tail yet shrouded in a vast ethereal coma of gas and dust that defied simple explanation. Its light curve suggested a solid tumbling body, a spinning shard of rock and ice. Yet the spectrographs from the James Webb Space Telescope told a far more intricate, almost fantastical tale, revealing a chemical bestiary in its tenuous atmosphere that simply shouldn't be there. The pieces of the puzzle lay scattered across 1,000 computer screens, each one glinting with a fragment of the truth but refusing to fit together. For weeks, the international consortium of scientists felt like they were chasing a phantom. Every new model they built, every simulation they ran, would crash against the rocks of observation. A model that explained the object's bizarre torqued rotation couldn't account for the sheer volume of its outgassing. A simulation that accurately predicted its chemical coma would fail to explain its remarkable structural integrity as it plunged toward the sun. It was an object of profound contradictions, a celestial chimera. The tension in virtual meeting rooms stretching across continents and time zones was palpable. They were witnessing the arrival of a truly unique messenger from interstellar space, and it was speaking a language they could not yet comprehend. The feeling was not one of failure, but of being on the precipice of a paradigm shift. The universe was showing them something new, something that had been missing from their grand cosmic theories. The breakthrough, when it finally came, did not arrive in a single blinding flash of insight. It was quieter, more methodical. It began with a subtle shift in perspective championed by a team at the Max Planck Institute. They proposed that everyone was making a fundamental error trying to find a single unified model for a single uniform object. What if they posited 3I? Atlas wasn't one thing. What if the contradictory datasets weren't contradictory at all? What if they were simply describing different parts of a complex composite body, a structure more akin to a planet than a simple piece of cosmic debris? It was a hypothesis that initially seemed to complicate matters further, yet it held a strange, compelling logic. It suggested that to understand this visitor, we had to stop thinking of it as a monolith and start treating it as a world in miniature with layers and internal dynamics all its own. This new lens brought the chaotic data into stunning focus. Suddenly, the spectrographic whispers from the JWST began to align with the radar echoes bouncing back from the Arecibo Observatory. The team in Hawaii, monitoring the faint polarization of light reflecting from the object's core, found their results snapping into place with the thermal imaging being analyzed in Chile. It was like tuning a vast planetary orchestra. For weeks, the instruments had been playing different melodies in different keys. Now, with this new understanding, a powerful unified symphony began to emerge from the noise. The scientists weren't just observing a rock, they were performing a celestial autopsy from 100 million miles away, peeling back the layers of this interstellar traveler to reveal the secrets it had carried across the unfathomable abyss. The first layer to be understood was its magnificent ghostly coma. For a typical comet, this gaseous shroud is a simple affair born from sun-warmed water ice sublimating directly into space. But the coma of 3I Atlas was far too rich, too complex. Webb's unparalleled infrared sensitivity detected the expected signatures of water and carbon dioxide, but it also found a staggering abundance of supervolatiles, frozen nitrogen, methane, and carbon monoxide. These are substances that boil away at incredibly low temperatures, suggesting the object had spent almost its entire existence in a cold far deeper than our own Oort cloud. It was a relic from the absolute zero of interstellar night. Even more profound was the discovery locked within this sublimating ice. Trapped like tiny ghosts in a crystalline cage were heavy, noble gases, xenon and krypton. Here in this single chemical fingerprint was a stunning clue to its birthplace. These gases are reluctant participants in cosmic chemistry. They don't easily bind with other elements. To trap them in the quantities observed requires very specific and extreme conditions, immense pressures, and frigid temperatures found only in the dense, turbulent, and frigid outer rings of a protoplanetary disk swirling around a newborn star. The specific ratio of these isotopes acted as a cosmic passport stamped with the unique elemental makeup of its home nebula. This was not the chemistry of our solar system. The ratios were alien. It was the first definitive proof that we were not just looking at something from far away, but something that was formed in a completely different stellar crucible, an alchemical furnace with its own distinct recipe for making worlds. 3I Atlas was carrying a chemical message, a primordial sample from a solar system. We will never see a time capsule from the dawn of another world, but this discovery only deepened the central paradox. An object so rich in supervolatile ices should be incredibly fragile. It should be a cosmic puffball, a loosely bound aggregate of frozen gases and dust. As it approached the sun, the searing stellar radiation should have acted like a celestial blowtorch, tearing it apart from the inside out. We should have seen it fracture break into a cascade of smaller fragments, or even dissolve completely into a streak of dust and gas. Comets from our own solar system, far more robust than this one appeared to be, have been destroyed by far less, yet 3I, Atlas, held together. It endured the rising thermal stress and the immense gravitational tides of the sun with a tenacity that defied all models of cometary physics. It was outgassing with the fury of a fragile ice ball, but it possessed the constitution of a solid rock. The answer to this riddle came from the ground, from the faint radio waves that pierced through the coma and touched the surface of the object's hidden heart. The radar telemetry was painstaking to collect and even harder to interpret. It was like trying to map the shape of a mountain in a hurricane by listening to the echoes of your own voice. But after weeks of signal integration, collating echoes from multiple observatories, a three-dimensional image began to resolve itself from the static. And it was breathtaking. The core of 3I, Atlas, was not the uniform porous rubble pile they had expected. The radar data revealed a clear internal differentiation. At its very center lay a dense, highly reflective core, estimated to be several kilometers in diameter. The signature was unmistakable crystalline silicates, the kind forged in the hot inner regions of a stellar nebula, interlaced with significant deposits of metallic iron and nickel. This was the anchor. This was the gravitational gyroscope that gave the object its stability. It was a solid rocky foundation, a planetary seed. Surrounding this dense core was a thick, porous mantle, a world-spanning crust composed of the supervolatile ices the spectrographs had detected. The structure was not that of a comet, but of a failed planet. The intense solar heat was not reaching the solid core. It was only touching the outer layers of this incredibly fragile, volatile, rich mantle. This porous, icy shell was sublimating violently, creating the immense, chemically complex coma. This process also explained the bizarre rotation. As jets of gas erupted unevenly from its surface, they acted like chaotic natural thrusters, pushing and nudging the object, causing it to tumble and torque in its strange, unpredictable dance. The object wasn't at war with itself. Its two contradictory natures, the solid core and the volatile mantle, were working in perfect dynamic concert. It was a celestial engine powered by the sun whose mechanics were finally laid bare. With this, all the scattered pieces on the board snapped into place. The chemical passport from the coma, the structural integrity of the core, the mechanics of its outgassing, they all pointed to a single, elegant, and revolutionary conclusion. The scientific teams, in a series of jubilant, sleep-deprived video conferences, began to construct the object's life story. This was not a comet born from the leftover scraps of a solar system. It was something far more significant. It was born in the turbulent, frigid frontier of a young, distant star system far beyond its equivalent of our asteroid belt. It began its life in the snow line, that critical border where volatile gases freeze into solid ice. The dense, rocky core accreted first, a gravitational seed gathering the silicates and metals from the primordial disk. Over millions of years, this core swept through the outer nebula, accumulating a massive mantle of the exotic ices that were plentiful in that cold domain. It was on the path to becoming the core of a gas giant, a nascent Jupiter or Neptune. It was a planetary embryo, but its destiny was violently interrupted. The simulations, now fed with the object's true mass and composition, showed only one likely scenario for its current trajectory. In its youth, its orbit was catastrophically disrupted by a much larger migrating planet, a hot Jupiter, perhaps carving a fiery path through its own system. In a gravitational exchange of unimaginable power, 3I, Atlas, was flung out of its home, a tiny orphaned world ejected into the lonely darkness between the stars. For billions of years, it drifted through the interstellar void, a perfectly preserved fossil of planetary formation kept in a state of cryogenic deep freeze. Its volatile mantle, which would have long ago boiled away in its own system, was protected by the absolute cold. It was a ghost of a world that never was, a cosmic messenger carrying the blueprint of its own interrupted creation. And here, in the grand synthesis of data from across the electromagnetic spectrum, was the climax, the eureka moment that would rewrite textbooks. The lead scientist from the Webb observation team, her voice thick with emotion, presented the final slide in a global address to the astronomical community. It contained no complex charts, no arcane equations. It was simply an artist's rendering of the object's interior, showing the dense, rocky core and its thick, icy mantle. For months, she began her image broadcast to labs and universities around the world. We have struggled with a definition for this extraordinary visitor. The evidence is now overwhelming, and the conclusion is inescapable. She paused, letting the weight of the moment settle. 3I. Atlas is not a comet, nor is it an asteroid in any traditional sense. What we are seeing is the pristine, exposed core of an infant planet. It is a planetesimal, the fundamental building block of a giant world torn from its stellar nursery and delivered against all odds to our doorstep. The statement hung in the air, a revelation of profound significance. We were not just looking at a piece of interstellar debris. We were staring at the raw materials of Genesis. For the first time, we could study up close the unprocessed heart of a planet from another star system. All our theories about how giant planets form, about the distribution of elements in a stellar nebula, about the chaotic violence of a young solar system, they were no longer just theories. Here was the physical proof, a tangible artifact of that process. 3I, Atlas, confirmed that the architecture of world building, the fundamental physics and chemistry is likely universal. The way our own Jupiter and Saturn were born is a process repeated around countless other stars. It was a moment of deep connection, a realization that the story of our own solar system is but one chapter in a vast galactic saga of creation. The confirmation of what 3I, Atlas is, has been a monumental achievement, a testament to human curiosity and technological prowess. We have intercepted a message from across the interstellar ocean, and after months of tireless work, we have finally translated it. But in solving one great mystery, this traveler has presented us with an even more tantalizing one. Its mantle is not just made of ice. It is a rich chemical soup brimming with complex organic molecules, tholins, the precursors to amino acids, and vast quantities of liquid water locked away beneath its surface. It carries all the fundamental ingredients for life, protected within its rocky heart and icy shell. The journey of this object proves that the building blocks of worlds are not confined to their home systems. They are cosmic driftwood, scattered across the galaxy by gravitational tides. And this raises a question that resonates deep within our own quest for origins, a question that will drive the next chapter of our exploration. If these planetary embryos are common, if the galaxy is filled with these wandering seeds, could they be more than just fossils of dead worlds? Could they in fact be the very vessels of life's propagation? Could an object just like 3I Atlas crashing into a young barren Earth billions of years ago have delivered the water to our oceans and the organic chemistry that sparked our own existence? We now know what this object is. The next far more profound question we must ask is, what does its presence here mean for us? And so the traveller recedes. Its light, once a beacon of frenzied scientific discovery, now fades back into the profound star-dusted blackness from which it came. The torrent of data that poured down upon us during those electrifying days in March has slowed to a whisper, a final ghostly echo of its passage. What remains is the silence. A silence filled not with emptiness, but with the weight of revelation. For we are not the same people who first looked up and saw that faint, anomalous speck. We have stood on a new shore and watched a vessel from an unknown continent drift by, and in its wake, our map of the universe has been irrevocably redrawn. The story of 3I Atlas does not truly end with its departure from our skies. It ends here, inside us, with a fundamental shift in our understanding of what the cosmos is and what our place within it might be. The journey to this moment was a breathtaking sprint against the clock, a race against the immutable laws of celestial mechanics. We chased a phantom through the void, throwing the combined might of our terrestrial and spaceborne observatories at a fleeting target. Every photon captured was a prize, every spectral line a clue in the greatest detective story of the century. You were there with us, watching as we sifted through the noise, searching for the signal. You felt the collective intake of breath as 3I Atlas prepared to make its historic plunge across the ecliptic plane, the grand flat disk where our own family of planets performs its ancient sun-drenched ballet. This was no mere flyby. It was an intersection, a moment of profound cosmic convergence where the plane of our existence was pierced by a messenger from another. We held our vigilance, wondering what secrets would be unlocked when this alien object was subjected to the full, unfiltered glare of our star. The answer, when it came, was more wondrous and more complex than our boldest theories had predicted. We expected a comet, perhaps an asteroid, built from the familiar chemistry we see in our own cosmic neighborhood. Nature, however, proved to be a far more imaginative architect. The light that reached our instruments painted a portrait of a truly alien world fragment. It was in the subtle yet undeniable isotopic signatures, the specific weights of the atoms locked within its outgassing halo. The ratios of xenon and argon were unlike anything ever recorded in our solar system, a ghostly fingerprint that did not match the primordial cloud from which Earth and its siblings were born. These were not the elements forged in our star's ancient stellar nursery. They spoke of a different parent star, of a different protoplanetary disk, with a unique chemical history and a different evolutionary path. This single piece of evidence shattered a comforting assumption that the basic building blocks of planetary systems were roughly the same everywhere. 3I Atlas whispered a new truth, that the galaxy is a mosaic of chemical provinces, each with its own distinct elemental dialect. The object's composition pointed not to a small rocky body, but hinted at a violent origin, suggesting it was shrapnel torn from the deep, volatile, rich mantle of a super-Earth or a mini-Neptune. It was a piece of a world, unlike any in our own solar system, a world with a dense, crushing atmosphere and exotic geology, which was shattered and flung into the interstellar dark by some long-ago gravitational cataclysm. We weren't just observing a rock. We were performing a long-distance autopsy on a piece of a dead alien world, a world we will never see but whose existence we can no longer deny. It was a tangible link, a physical relic, proving that the types of worlds we are just beginning to glimpse around other stars are not just theoretical points of light. They are real physical places forged and sometimes broken by the same universal laws of physics. Then came the interaction with our sun, the true climax of its March crossing. As 3I Atlas sliced through the ecliptic, it flew directly through the densest part of the interplanetary magnetic field, a vast invisible structure that flows outward from our star like a celestial gale. We expected to see its tenuous atmosphere battered and shaped by this solar wind, a classic comet-like interaction. But what we saw was stranger. The object's own localized magnetic field, faint but distinct, resisted the sun's influence in a way that defied our models. It wasn't a passive victim of the solar storm. It was an active participant, a gravitational gyroscope wrapped in a magnetic shield of its own making. This anomaly forced our plasma physicists and astronomers into a frantic collaboration, rewriting theories on the fly. It suggested a composition rich in certain conductive materials magnetized over billions of years while orbiting its parent star. A star perhaps far more magnetically active than our own placid Sunday. This object carried with it not just the chemical memory of its home, but a fossilized magnetic imprint, a paleomagnetic record of another star's environment. The legacy of these discoveries is profound. For millennia, humanity has looked at the stars and felt an immense, overwhelming sense of isolation. The distances are too vast, the gulfs too wide. We were an island universe adrift in an endless empty ocean. 3I, Atlas, demolished that conception. It proved that the ocean is not empty. It is a dynamic, interconnected system. The galaxy is not a collection of isolated islands, but a grand archipelago where material is constantly exchanged. We are downstream from countless other solar systems, and they are downstream from us. The flotsam and jetsam of planetary formation, the very building blocks of worlds, are sailing on the slow, patient currents of galactic gravity, making journeys that last for millions, even billions of years. For the first time, we can say with certainty that we live in a shared galaxy. The materials that form a planet around a star in the Orion Arm could, after a long and meandering journey, end up falling into the atmosphere of a gas giant in the Sagittarius Arm. This realization is not merely academic, it is deeply personal. It reframes our entire existence. It means the boundary of our solar system is not a wall but a permeable membrane. We are not alone even if we have not yet found intelligent life. We are part of a cosmic ecosystem, a galactic community of matter. The iron in your blood, the calcium in your bones was forged in the heart of a long-dead star. We have always known we are made of stardust. But now we must grapple with a new reality. Some of the atoms on a distant alien world may have originated in the very same supernova that seeded our own solar system, and now a piece of their world has visited ours. This is a form of contact, not of minds, but of matter. It is a physical handshake across an unimaginable expanse of space and time. It deepens the mystery, expands our perspective, and forces us to see our home not as a fortress of solitude, but as a port of call on a vast galactic ocean. This single visitor has ignited a revolution, forcing us to prepare for the next. The age of passive observation is ending. The age of active interstellar search is beginning. We can no longer be content to stumble upon these travelers by chance. We must build the tools to hunt for them systematically. On a remote mountaintop in Chile, a new eye is opening to the cosmos, the Vera C. Rubin Observatory. This is not just another telescope. It is a celestial net, a sentinel designed to scan the entire visible southern sky every 3 nights. Its vast digital camera, the largest ever constructed, will create the deepest, widest movie of the universe ever made, cataloging billions of objects and watching them move. Within this immense river of data, its powerful machine learning algorithms will be trained to do one thing with ruthless efficiency: spot the outliers. They will search for the faint specks moving too fast on the wrong trajectory with the telltale hyperbolic orbit that screams intruder. Where we once found one interstellar object per decade, by luck, the Rubin Observatory is predicted to find dozens every year. We will move from an era of scarcity to an era of abundance. We will begin to build a true statistical census of these galactic wanderers. Are they all like Oumuamua, strange and inert? Or are they like 3I, Atlas, chemically rich and magnetically active? Or are they something else entirely? We will finally be able to determine if our solar system is typical or atypical in the kinds of materials it ejects into the void. Each new visitor will be another page in a grand accumulating encyclopedia of the galaxy's chemistry, dynamics, and history. We will become galactic archaeologists, piecing together the story of our cosmic neighborhood from the fragments that wash up on our shores. but seeing them will no longer be enough. The tantalizingly brief encounter with 3I, Atlas, has instilled in us a burning desire to do more than just watch them pass by. It has given birth to a new audacious dream, the chase. Missions are now being designed, conceptualized on digital drawing boards at space agencies around the world for a new class of probe. These will not be lumbering explorers on decade-long journeys to our neighboring planets. They will be cosmic sprinters, lightweight, powerful spacecraft kept in a state of constant readiness, waiting on the ground or in a high Earth orbit. They will be our rapid response team. When an object like 3I, Atlas, is detected with its trajectory confirmed, these probes will launch on a moment's notice. They will fire powerful next-generation engines, solar, electric, or perhaps even nuclear thermal propulsion to embark on a high-speed intercept course. The challenges are monumental, demanding a level of autonomy never before seen in a space probe. The craft would need to navigate on its own, making real-time course corrections as it closes in on a target that is itself moving at incredible speed. It would have to approach an object whose size, shape, and rotation are completely unknown, deploying its own suite of instruments, spectrometers, magnetometers, high-resolution imagers, to perform a close-up analysis in a matter of hours or even minutes. It would be a fleeting, high-stakes encounter, a daring flyby that would transform a distant point of light into a detailed three-dimensional world. We would no longer be analyzing the faint reflected sunlight from a billion kilometers away. We would be there flying alongside it, tasting its chemical breath and mapping its alien shores. We would be sending our robotic emissaries to greet these travelers at our doorstep. Even that grand ambition, however, pales in comparison to the ultimate prize, the holy grail of interstellar exploration that 3I, Atlas, has brought from the realm of science fiction into the realm of possibility, a sample return. Mission. Imagine not just visiting one of these objects, but bringing a piece of it home. A mission profile of breathtaking complexity would be required. An interceptor spacecraft would have to match the object's incredible speed, a feat of orbital mechanics at the very edge of our technological capability. It would then need to approach the body and, without landing, deploy a collector, perhaps a sticky aerodynamic gel or a harpoon-like penetrator to capture a few precious grams of surface material. Dust ice, organic molecules, a physical piece of another solar system. Then the even harder part begins, the return journey. The probe would have to fire its engines again, not to slow down, but to bend its trajectory just enough to eventually swing back toward Earth, a journey that could take decades. Finally, a small, heavily shielded capsule would detach, screaming through our atmosphere at blistering speeds, before deploying its parachutes and landing gently in some remote desert. Inside that capsule would be the most valuable scientific treasure in human history. For the first time, we would have alien matter pristine and untouched in our laboratories. We could subject it to the full power of our analytical instruments, probing its atomic structure, decoding its isotopic history, searching for complex organic compounds. We could hold in our hands the very building blocks of a world that formed around another star. The questions we could answer would be fundamental. Is the chemistry that led to life on Earth common throughout the galaxy? Are the seeds of biology universal carried on these interstellar messengers? This is the legacy of 3I, Atlas. It arrived as a silent traveler, and it leaves as a catalyst for our future. It was a single data point that bent the curve of human history, a cosmic messenger that delivered a startling and inspiring new chapter in our quest for understanding. For thousands of generations, we have stared into the night sky and asked the same fundamental questions. Who are we? Where did we come from? Are we alone? We look to the steady, unblinking stars for answers, seeing them as beautiful but unreachable fixtures in a static diorama. That era is over. 3I, Atlas, has taught us that the sky is not a static portrait. It is a living, breathing, interconnected space full of motion and history. The stars are not just destinations, they are origins sending pieces of themselves out to wander the great dark expanse. The human quest for knowledge is as relentless as gravity, always pulling us toward the next frontier. We built telescopes to see farther. We built rockets to travel higher. And now, inspired by a fleeting visitor from an unknown star, we are designing the nets and the ships to welcome the next one. We will continue to look up, not just with wonder, but with anticipation, knowing that the universe is not just something to be observed, but something that actively visits us. The story is not over. The silence left in the wake of 3I, Atlas, is the quiet before the dawn of a new age of discovery, an age where we finally begin to read the scattered ancient language of the galaxy, one messenger at a time. The journey has just begun.